request Antonio. So Antonio is a faculty, he's from Faculty of Engineering in the University of Sydney. So Antonio is also an associate editor of the Chemical Engineering Journal. This is his journal for many of the chemical engineers to publish in. And he has research is focused on light matter interaction over multi-scale interfaces for the design and innovative materials and devices with application in personalized medicine and also renewable energy. And he has his PhD from ETH Zurich, and he has also received a Best Thesis or Best Innovation Thesis Award in ETH Zurich. And he has received several fellowships, including the Australian National University Leadership Fellowship, and also the Australian Research Council Discovery Early Career Award is also given to him. And 2020 ERC Future Fellowship is also given. It was nice having Antonio here. Yeah, please.
So, good morning or good afternoon, everyone. It's a great pleasure to be with you in Chile. It's my first time in India, and it's been a very nice experience. I'm very happy to be here. Before I start speaking about science, I usually have a slide to try to invite people to join us in Australia. Australia is very beautiful. I arrived there about 2 years ago from ETH Zurich, and I still have not left. And Switzerland is not too bad either. Right? So please come and visit. I established my lab since 3 years at the University of Sydney. Before I was at the Australian National University. We are still growing there, and we work on quite a broad range of activities. So perhaps some of you that may not work on hydrogen or about what we talk today, maybe still find interesting to visit us. My group focuses on one concept. So often we discover interesting materials, more often nanomaterials. But then when we go and try and trap them in a device, they often don't work as we want. We talk about graphene, carbon nanotube, and many others. And so my question is, how do we structure them? How do we go across the scale so we can reach the properties of a nanomaterial in the device? And this applies to many things. You can go to microbial proteins, biomaterials, sensor. That's actually a hole in the water back my nanomaterial. And today I'm going to talk about energy conversion and storage. So the motivation for this is something that we all know, but I think it's always important to repeat it. In the last 80 years, CO2 emissions have increased dramatically. The concentration of CO2 has increased by about 50%. And now we have reached, in function of that, almost an increase of 1 degree in the temperature of our planet. The frequency of extreme events, take flooding, such as one we have experienced recently, but also in Sydney, in Australia, we experienced them very frequently, or drought is increasing dramatically. So we have to take action. And the best action is to stop using fossil fuels if we have a replacement for them. That's not always the case, but if you look at the installation of renewable energy across the world, you can go from concentrated solar panels to either to turbine, wind turbine, or photovoltaic more and more. It's increasing dramatically. That's a great news, especially when we look at the ratio between fossil fuel generating electricity in gray and renewable energy generating electricity power installed new every year. And if you look at that, in 2014, we're already installing as much renewable energy generating power as fossil fuels. And nowadays, actually fossil fuels is just a small fraction. So that's great. But this trend has some problem and cannot keep going. One major issue is that it's destabilized the grid. Obviously, when we have lots of wind or light, we have lots of energy. What happens when we're not, right? And one way to solve this problem is to have storage. In Switzerland, there is a lot of hydro pump storage. It's great. When you have a lot of electricity, you can pump it up. This is not always a good solution because fresh water that is required for that is also an important resource for the planet. And many people don't have access to it. Also in some countries, like Australia, we don't have that much freshwater resources that we can use this way. So an alternative to that, I mean, obviously use it if you can, is to have chemical energy storage. The concept is simple. There is another problem. Also, another problem is where do we produce the renewable energy? If you look at solar energy, which is one of the most abundant renewable resources, is mostly concentrated in area like Australia, South America, part of Africa. That if you look at the population density, is where you have the least people. So if you use PV to produce electricity, we cannot use it there. We have to export it. And we should export it to countries like India, part of Asia, Europe, where we have so many people that it's very hard to install solar panels because they compete, for example, with agriculture, like in Italy. A lot of old plantation have been replaced by PV, which are against, right? So how can we transport it and also store it? Well, we can do chemical energy storage. We can take directly light, like Francois was mentioning before, or electricity generated by various means, make a fuel such as ammonia, hydrogen, store it, bring it back, and close the circle. A great example would be hydrogen, because we can already produce hydrogen with more than 85% efficiency using electrolyzer. We are actually, you can use PV panels, which is the cheapest way to produce electricity to run these electrolyzers, right? And we are working more and more, we are getting close to things that can enable us to transport hydrogen. However, this is not reality. For now, it's just a dream. 95% of hydrogen is produced from fossil fuels, basically by reforming of methane. This has a huge footprint, a CO2 footprint, and does not solve the problem. Why is the case? It's just because it's too expensive and it's not scalable. So if you look at the electrochemical production of hydrogen, where we basically take a water molecule and we split it in oxygen and hydrogen, having the HCR or ER reactions, it's a quite simple process, but it actually has a very high activity barrier. So we need a catalyst to bring this barrier down, else we waste a lot of energy and heat in trying to break the water molecules. Now, I mentioned before, this can be done efficiently, it's true, if you use things like ruthenium, platinum, iridium, which are very expensive, and also not abundant. 2009, 30 tons per year of ruthenium actually is not much more now. And so the problem is, can we create catalysts? So can we catalyze the hydrogen production, rotary fuels, using not these materials here, which are the rarest in the world, but actually rock-forming elements, such as iron, cobalt, and things. It looks like, there are several orders of magnitudes here. We are scientists, we don't look at them anymore. Yes, whatever, 10 to the 6. Let's talk about money. I think we all understand that. If you use 1 ton of platinum, it costs you 37 million. This kind of catalyst. If you go to cobalt and nickel, which are now increasing because of the use of batteries, or EV mostly, it's about 35,000. And if you're able to use iron, it's all $100 per ton. So not only we can make it cheaper, we can make it also very scalable. Now, what's the problem? And how does it go back to my research? Is that when you use something like iron magic, it likes to oxidize, very poor conduction, not stability, not high active surface. It's very hard to engineer it. So you have to find a way to go all the way from the surface properties you want into how you manage electrolyte, fuel transport, and electric transport. So I call this multi-scale engineering of electromaterials. Right? Now, there are various ways to do that. My group specializes in a process called fractal self-assembly. Why is that? Because even if you were to use lithography or very strongly controlled top-down approaches, it's very hard to scale them up. If you use something like plants use, fractal, self-repeating units over scale, if you have the right self-assembly mechanism, we can make tons. Now, one way to make these films with self-assembly electrodes is using aerosol. Imagine aerosol, like when it's done, you produce nanoparticle catalyst, you let them settle down. And if you do that, can you press on this video, please? This is a particle dynamic simulation of what happens when a nanocatalyst of 50 nanometer approaches a surface, you make a fractal structure, which repeats again and again with the same properties. I can shape the building, it will have the same properties. And it can be done on very large surface, as shown for mountains, where actually there's no crystal, basically cut them all, right? Now, this is an example of a fractal structure deposited by aerosol deposition of nanocatalysts. It's very porous, 98%, and it reminds you of the simulation I just showed you before. But how do we do this? Catalyst is only important. So we have a method to fabricate them, but how do we synthesize them? Well, one way is to use flames. Flame synthesis is very ancient, goes in old Asian paintings, and has been developed to produce carbon black, which is about 3 to 4 kilos of nanoparticle in non-tire as car tire, to P20 fumed silica, and titanium pigmentary, which is the base of all paint. So it's produced in megatons per year. So now if you use flames, we have a method to scale up electrocatalysts at a global scale. And this is the flame in the lab. It's called a flame spray pyrolysis system, which basically enables us to enable us to use a liquid solvent, put as many metal, salt in it, and then atomize it. That's the noise. This is the atomization, and make small droplets that we ignite. And then we have a reactor that runs at about 2,400 degrees, and it can continuously produce in this small space this small nanocrystal. Not only you can produce them, they are highly crystalline, as you can see there, so you don't need post-processing in principle. And we can control very well the structure, the the size, and the structure. And we get polymorphs of manganese oxide. We can go all the way from 12 nanometer to 22. We can control the specific surface area. So how much surface area per gram is an important characteristic for catalysts, right? And we can go all the way from few 30 square meter per gram to more than 120 square meter per gram continuously. And when you look at that and you put it in water with the sacrificial atom that makes your electrons, we can really split water and produce oxygen, right? Obviously, it's oxygen. And if you compare it to commercial catalysts, it's hundreds-fold better because of their area, very specific surface area. But not only. We can only control crystal structure. And as you can see here, different polymorphs with the same area have different performance. So we can do lots of fundamental studies. Lastly, I wanted to show you one thing about this method too. It enables us to control the porosity of the soil. Now I'll show you this very porous structure. Actually, it's not very robust. But by sintering in situ during deposition, we can go all the way from 98% to 12%, making very strong layer, and see which one are the most performing in terms of porosity. We can also deposit on porous substrate. This is a carbon fiber paper. And here we deposit bismuth nanoparticle, bismuth oxide, which are good for another catalytic purpose. So CO2 electroreduction, in this case, to formate. So you can do actually catalysts for a variety of issues. In the past 10 years, we have been investigating all these materials by flame synthesis, trying to combine them, trying to find the best electrocatalysts. And there are too many possibilities to show you all of them. I'm going to show you two of the best one, in my opinion, which are cobalt-based and iron-based. Also, they're cheap. This is an example of very thin layer of cobalt oxide nanoparticle with a very high surface area. We are above 100 square meter per gram, deposited in 5 seconds only on a substrate, conductive substrate. And then we can increase the time. Now, what you expect is, if you increase the time, your activity goes up. You produce more because you have more surface area. However, this is true only up to a certain time. When your thing gets too thick, I will show you here, then you have only dead catalysts. You're wasting your material. And this is because oxides have a major issue. They are not very good conductive. So we try to modify this, and this is an example where we dock the same catalyst with tungsten. A little bit of tungsten, about 6%. Set the onset potential, so where you basically start producing hydrogen, which put the water, in this case oxygen, and increase the current a lot. You can use it for both reaction, water oxidation and hydrogen evolution reaction. It works for both. And then we were trying to understand why does it happen. Is it the surface? Are we changing it? Actually, we characterize our material very well. They are basically identical from a crystal structure, just a bit distortion because of the incorporation of the tungsten. And we performed the in situ study. This is in situ Raman during electrochemistry, OER reaction, and HR. And we can see that something is changing in the surface. Well, that's well known because actually the cobalt oxide produced cobalt oxide and cobalt hydroxide during OER and HR reaction. We went to the synchrotron to perform in situ study. We confirmed this, so this surface basically are the same, and they are not the original cobalt oxide. So there is no tungsten interfering. So what is doing all of this is actually this post-mortem analysis showing the oxide layer of your particle. And what is doing all of this is the conductivity. Look at the huge change in impedance from the cobalt to the top cobalt oxide. Now, finally, is tungsten the best? So we started exploring a lot of dopants. Here is just an example, antimony and molybdenum. And as you can see, it gets better and better, and actually molybdenum is working quite well. So now we have an alkaline electrocatalyst, which work well for OER and share reaction is quite cheap. But we are reaching the limitation. It's very hard to push it further, and in my opinion, it's still not good enough. So we switch the gear and we say, okay, why don't we forget about these oxides and we go to the phosphides? Because the phosphides can be much better conductor than oxide. Plus, you have multiple opportunities to change the surface activity and properties inside, right? So we use the flame, and we're still working on produce them directly. For now, we use the flame to produce the oxide, and then we convert them in phosphides. And this is an example of a 15 centimeter wide nickel foam, where we in one step, few seconds, deposit our iron oxide, and then we convert it directly in a phosphide. You can see that the elemental characterization shows that it's mostly converted, only little oxide reoxidizes on the surface, and the porosity is preserved after this process, so we have a very high area. And when you look at the performance, that's actually quite stunning. Black is the nickel foam. Nickel is actually a catalyst, not much okay. We phosphodize the nickel foam, nothing happened. We put the iron oxide, looks a bit better. We convert it into phosphide, boom. Amazing, right? So we can increase dramatically the OER and HER activities, OER, HER, all over metals. And if you look at the performance over time, it's quite good, just few hours. That looks for hundreds of hours, very, very stable. So these results were very encouraging. So we went into look into industrial relevant conditions, which usually are not at room temperature, in black, but at 80 degrees, and with very high alkaline conditions, 6 mole of KOH. And you can see here, we only need a very small overpotential of 200 millivolt to produce 0.5 milliamp per square centimeter. Right? So this catalyst is excellent. Also for the HR reaction, very similar story. Right? So we went into integrating it into a small electrolyzer, and we were able to produce hydrogen with 85% terminator efficiency with something based on iron, which is $100 per ton, and phosphide, which is about $300, $400 per ton. So actually, very proud of this result. We went into scaling it up. Can you press the video there? And this is a foam of nickel foam. This is our flag. And this is a roll-to-roll setup where we can continuously coat this roll of electrocatalysts. And eventually, we hope we can actually supply to the global community for hydrogen production. And with this, I'd like to thank you for your attention. I hope I could show you that it is important to engineer the materials property all over the scales if you want to use something cheap, unless you have so much money that you don't care about it. And I hope that I show you a catalyst which has very strong potential for global hydrogen production. With this, please come to visit us in Sydney, and I would like to thank my group and all the funding we have received this year.
Thank you. I think we are running out of time, so we will not take a question now. We will take a question during lunch time. So before we break, I think appreciation would like to